All right, so we've learned a little bit about the semantics of Leibnizian modal logic. So now let's see what it's like to develop and use a derivation system in modal logic. So in order to do derivations in modal logic, we need to extend our language to include inference rules that permit us to work with the modal operators, box and diamond, just like we did with existential and universal operators when we developed predicate logic. So theoretically, we can add any rules we like, but since our aim is to create a proof system that reflects the semantics, that is, the meaning of the modal operators, then we should only add rules that we can prove using the semantics. So we will not prove all the rules we adopt, but it's important to understand what we are saying here. So if we drop back to the beginning, think about propositional logic proper, we might ask this question: where did our basic inference rules like conjunction introduction and conditional elimination come from? The answer is that they came from the semantics, which are displayed in the truth tables. So the rule of conditional elimination tells us that from any two formulas of the form A, and if A then B, we may infer B. And this rule reflects the following truth table. Now, this truth table could also be written differently as a theorem, and in this case the turnstile would be all the way over here on the left, and the corresponding validity is if A then B, and A then B. That is a validity or a tautology. So either way, the truth table shows that this is a valid argument form or a necessary truth, depending on how you want to think about it. Considered as a valid argument form, it shows that there is no interpretation in which the premises are true and the conclusion is false. And if we represented it as a tautology, it would show that it is true under every interpretation by T occurring under every box under the main operator. So that's old hat. So although in modal logic we can create truth tables for a particular model, V, we do not base inference rules on a particular model, but on the valuation rules for modal propositional logic itself. This means that any rule we adopt must be derivable from the valuation rules in the definitions, some of which we discussed in the previous lecture. One of the rules we'll adopt is this: necessarily A, therefore A. So this says something quite obvious, namely that necessary truths are true. But in order to justify adopting it, we need to be able to provide or prove that if necessarily A, then A is a validity, using the evaluation rules in our semantics. So the proof is similar in style to the proofs we did in the previous lecture, except that it proceeds as a reductio ad absurdum, which we also call negation introduction when we're doing formal proofs. This means that we assume that the premise is true and the conclusion is false, and then attempt to derive a contradiction. So let's recall the evaluation rules in the semantics for the modal operators. This is Rule 11 and Rule 12 in the text. And it says that given any Leibnizian valuation V for some world W in the worlds of V, Rule 11 says the value of box A, necessarily A at some world, is true if and only if for all worlds U in the worlds of V, the value of A, U, is true. And correspondingly, the value of necessarily A at W is false if and only if for some world U in WV, the value of A at U is not equal to true. Rule 12 provides the rules for the possibility operator, rules of interpretation, and it tells us that the value of diamond A, possible A, at world W is true if and only if for some world U in WV, the value of AU is true, and it tells us that the value of possible A at that world is false if and only if for all worlds U in WV, the value of A at U is not equal to true. Once again, the importance of using not equal to true here and here is that there are times when the rules don't tell us whether a proposition is true or false in a particular world because the proposition contains a name that does not refer to an object in that world. So when that happens, we can't infer that it is false, but we can infer that it is not true. So how do we prove in semantic terms that box A, necessarily A, implies A? Well, it's a little cumbersome, but it goes like this. Assume that for some valuation V and some world W, the value of necessarily A at W is true, and the value of A at W is not true, right? So this is the reductio assumption. We assume that in some world, necessarily A is true, and that A is not true. Well, now we're looking for a contradiction. Well, by Rule 11, which we just stated above, the value of necessarily A at W is true if and only if the value of A at U is true for all worlds U in W. So the value of necessarily A in any world is true if and only if the value of A is true in all worlds. Hence, the value of A at W is true, which contradicts the assumption. So this is just a very formal way of saying, look, if necessarily A is true, it's because A is true in every world, therefore A must be true in any world. So the text gives us 7 rules for modal logic. But one, the necessity of identity, we will ignore for now, since identity statements only arise within predicate logic, which we are going to avoid for a bit. So the remaining 5 rules are the K rule, the T rule, S4, Brouwer, and necessitation. So we're adopting all of these rules whole hog as our basic system of Leibnizian modal logic. So let's make sure we understand each one. Duality represents that equivalence relation between the two operators that we talked about in the last lecture. Necessarily A is logically equivalent to not possible not A, and possible A is logically equivalent to it's not necessarily the case that not A. That's the only equivalence that we work with. The K rule, which is very important, tells us that if it's necessarily the case that if A then B, then if it's necessarily A, the case that A, then it's necessarily the case that B. So it's a way of taking a boxed conditional and distributing the box to both the antecedent and the consequent. This is only for the conditional. It doesn't work for anything else. At least it's not a rule for anything else. And although we could prove this semantically, formally, we can appreciate it informally like this. Suppose it's necessarily the case that if A then B, well, what does that mean? It means that if A then B is true in every world. Well, if it is the case that if A then B is true in every world, then what happens if you assume that necessarily A? Well, that means that A is true in every world. And since if A then B is true in every world, then B is true in every world, which means necessarily B. The T rule we just discussed already. The S4 rule kind of takes us in the reverse direction of the T rule. It tells us that if it's necessarily the case that A, then it's necessarily the case that A. So how can we see that informally? Well, hypothesize that it's necessarily the case that A. That means A is true in every world. But if A is true in every world, then necessarily A is true in every world. Hence, it's necessarily the case that necessarily A. The Brouwer rule, which is named after a famous logician named Brouwer, tells us that if A, then it's necessarily possible that A. Well, why should we accept that? Well, think of it this way. If A is the case in some world, then possible A is true in all worlds. And if possible A is true in every world, then it follows that it's necessarily possible that A. So all of these are actually pretty transparent. The last rule is necessitation. All right, so let's prove some stuff. So let's prove that P yields possible P. That's transparently obvious. If P is true, then possible P is true. But it's not a rule. We don't have a rule like that. We have a rule similar to that, though, and it's called the Brouwer rule, right? And it tells us that if we have P, or any formula whatsoever, then what follows is necessarily possible that P, right? So that's 1 and the Brouwer rule. And then we can infer possible P from which rule? From 2 and the T rule, right? The T rule tells us that if necessarily A, then A, and in this case, possible P is our A. So that's a super simple proof. What if we had done the same proof but approached it differently? Suppose we had decided to do it through a negation introduction. So we'd say 2, it's not possible that P, hypothesis for negation introduction. Remember, we bring all these truth methods along from propositional logic. And what does not possible P tell us? Well, we have the dual rule that tells us that that tells us possible P is identical to necessarily not P, and then we have another not right here. So that's 2 and dual. And then by double negation, we have necessarily not P, and that's by 3 and double negation, from which the T rule allows us to derive not P. So that's 4 and T, and then you see we have a contradiction, and you can see how we finish that up. So proofs that are really simple in propositional logic can require some insight in modal logic. For example, in propositional logic, it's completely trivial to prove that P and Q yields P, but how do you show that necessarily P and Q yields necessarily P? Well, the text explains the standard approach. The necessitation rule allows you to introduce any derived theorem as a necessary truth. So if we have previously proved something like if P and Q then P as a theorem, then we're entitled to introduce necessarily if P and Q then P on any line by the end rule. Now, this, of course, is where you need a book of theorems all numbered so that you can cite them, and the text is such a book. But let's assume we've proved this theorem, which we probably have, and try using it to do the proof. So we know that, we assume that necessarily P and Q, and we know that it's necessarily the case that if P and Q, then P, because if P and Q, then P is a theorem proved in propositional logic, and the end rule, which does not cite a line, by the way, allows us to assert that with a box. So necessarily, if P and Q, then P. Now, what do you think is going to get us somewhere here? Well, it's the other rule that we haven't used yet, the K rule, which allows us to distribute this box to the antecedent and the consequent. So this is how this works. Necessarily P and Q, then necessarily P by 2 and the K rule. And then we have our old friend, conditional elimination, which gives us necessarily P by 1, 3, conditional elimination. Okay, so this basic method of proof turns out to be super important and common in Leibnizian modal logic. So there are lots of different proof systems under the general heading of Leibnizian modal logic, some of which introduce other symbols and methods of proof. This system is pretty minimalistic, and doing proofs in it often depends on the creative use of the K and the N rules. In general, the way you need to think is to come up with a theorem in propositional logic for which an assumption you have available in the proof is the antecedent condition, and for which the consequent is some woof that you are trying to derive. So how would you do this one? Necessarily P, then necessarily P or Q. That's a lot like the one we just did, so it would be a good idea for you to figure it out. So hopefully you've taken some time to do so. Right, so on line 1, we have necessarily P as an assumption, right? And I noodle about this a little bit, and I realize that, hey, if P is true, then P or Q is true. That's certainly an easily proved theorem. So I'm going to assert necessarily if P, then P or Q by the N rule. Then with K, I'm going to get necessarily P, then necessarily if P or Q. That's 1, that's 2, and the K rule. And just like before, right, I have 1. Now what you might be thinking here is, you should really be thinking here is, well, wait a minute, I mean, obviously, are you just going to take my word for it whenever I assert that something is a theorem? And the answer is no, only when it's kind of perfectly obviously provable. But if you assert something as a theorem, which isn't, then of course it's going to be wrong. And if you assert something as a theorem that is not obviously a theorem, then you're going to want to derive it on the side as part of the solution to the problem. So S4 tells us that if P is necessary, it is necessarily necessary. So is there a parallel relationship with possibility? In other words, does the fact that P is possible imply that it is possible that it is possible? Certainly sounds reasonable. So let's try to prove that. So let's try to do this one by negation introduction. And so we assume that it's possible that P, and we hypothesize for negation introduction that it's not the case that it's possible that. Well, maybe you can see how this is going to go. You should certainly try, right? So you've got line 3. You're looking for a contradiction. How about necessarily possible that it's possible that P by 1 and which rule? The Brouwer rule, right? That gives us possible that P by 3 and the T rule. Here's your contradiction, and that's all there is to it except for the formalities of negation introduction. How about a different approach to the problem? So how about on line 3, we take advantage of the N rule, and if we did that, we would get it's not the case that not necessarily not possible that P, right? We're substituting not necessarily not for the first possible, for the first diamond. Sorry, I said the N rule, but it's really dual, right? 2 dual. And then just double negation will give us it's not necessarily not possible that P. So 3 double negation. That gives us not possible that P. So 4 and which rule? The T rule. And there's your contradiction between 1 and 5. And once again, just the formalities of finishing off the negation introduction proof. Now, we might suspect that possible P and possible P are logically equivalent. So if so, then we should be able to do the proof in the opposite direction, right? So we should be able to prove if possible P, then possible P. So this is another one that you're going to want to pursue via negation introduction. And a nice little shortcut here is to realize that since it's not the case that possible P, right, is logically equivalent to necessarily not P, and necessarily not P is very often what you really want to work with anyway, then you could just start by hypothesizing necessarily not P. So suppose we hypothesized that necessarily not P, hypothesis or negation introduction. Well, it's not obvious what to do from here, right? I mean, there's two things that you might try to do to build up another operator, because this is what you're going to need to do to contradict possible. Notice that there's nothing you can do really to possible P, right? I mean, you could go, okay, that means not necessarily not possible P, but you can't infer anything from this because there's a negation here. So that is not a productive use of our time. You gotta look at it and try, obviously, before you can see that. But remember, there's another way to add an operator, and that's with S4. S4 allows us to go necessary, not P, right? If you have a formula whose main operator is the box, you can add another box to it. So that might be productive. Let's try that. So that's going to be by 2 and S4. And now maybe dual will help us get something done. Right, so now we can go box, not possible, not P, by 3 in dual. And then we could apply double negation to get necessarily not possible that P, right? So that's just 4 in double negation. And then on line 6, you can get not possible, not possible P, again, this time by 5 and dual. So go ahead and throw in a little Q and not Q with con, just so you don't have to write all those operators out. And finish it up in the usual way. Not necessarily not P, and that by dual converts to possible P. So it's important to remember that every proof you do can be material for later proofs through the necessitation rule, N. Now we've just proved possible P yields possible P, and this is equivalent to having proved the theorem, if possible P, then possible P. Since this is a theorem, then we can assert it at any point by theorem introduction, TI. Now, this may be the first time you've heard of this rule, but it is part of the system and one that we should be mature enough in our logical faculties to deal with responsibly at this point. So theorem introduction, TI, tells us that you can introduce a theorem at any point and just call it a theorem. And if it's not perfectly obvious that it's a theorem, then of course, just like with N, you'd have to derive it on the side. Okay, so you have two possibilities here. Theorem introduction, which is really just part of propositional and predicate logic, which allows you just to introduce the theorem itself, and then N, which allows you to assert the theorem as a necessity. So both of these can actually be quite useful. And besides its commitment to the existence of possible worlds, Leibnizian modal logic is interesting because it permits some rather unintuitive inferences. For example, while it's very intuitive that necessarily P implies P, we might balk at the suggestion that possible necessary P implies P, right? It's not at all obviously correct. If it's possible that it's necessary that P, then P. Now this has a long and hoary presence in philosophy because it relates to a particular proof of God's existence, the ontological proof. So if we were to let G stand for God exists, then necessarily G says that it is necessary that God exists. Now, suppose you don't know about that, but you are willing to countenance that it's logically possible that God exists necessarily. In other words, you allow that it's possible that necessarily God exists. Well, in Leibnizian modal logic, it can be shown that you've just allowed that God does indeed exist. The mere possibility of his necessity implies his actuality. So let's see if we can prove that possible necessarily G implies G. All right, so this actually proceeds very straightforwardly. There's nothing you can do to the assumption that's going to be productive. And in general, it's important to point out that there just aren't any rules for operating on formulas where the possibility operator is the main operator. So very often you're looking for creative workarounds for that. So the obvious thing to do here is, of course, just hypothesize it's not the case that G, and then even just sort of at a qualitative level, you can see that your best bet here is going to be to use the Brouwer rule and try to massage a contradiction out of that. So if we know that not G, we know that necessarily possible that not G by 2 in the Brouwer rule. And so now you've got possible necessary in the assumption, necessarily possible not on line 3, and if you apply dual and double negation a couple of times, you're going to end up with a contradiction. Like so. So contradiction between lines 1 and 7, and we've finished it up in the usual way. That's a very straightforward proof to a pretty surprising conclusion, at least on the face of it. Of course, this merely shows that God exists, not that he exists necessarily as the necessary being that theologians have fantasized about. Is it possible to prove something even more counterintuitive, namely that if it is possible that God exists necessarily, then he does exist necessarily? So does the mere possibility of necessary existence imply necessary existence? This actually just doesn't seem right. It's definitely not generally the case that possible P implies P. It doesn't follow from the fact that it is possible that I'm a millionaire, that I'm actually a millionaire. On the other hand, consider this. You just proved that if it is possible that God exists necessarily, then God actually exists, meaning that in our world, God exists. But now consider the fact that this proof can be performed in any world. So if God's necessary existence is possible in every world, it looks like he exists in every world, which means that he necessarily exists. So before we try proving this result, let's consider this more basic question. Recall that the Brouwer rule tells us that P yields necessarily possible P. You might think about this as follows. We've already shown that P implies possible P, so the Brouwer rule seems to be telling us that just as things don't just happen to be necessary, they don't just happen to be possible either. If that's right, maybe the Brouwer rule itself will help us to prove this. Possible P, therefore necessarily possible P. Now, with a proof like this, you would probably find yourself wanting to start again with a negation introduction. But if you negate the box, right, like that, then your obvious next step is to apply dual, and you're going to get a formula where the diamond is the main operator. And as I just said, there's not a whole lot you can do with formulas like that. So let's not do that. Let's try really stacking up the operators and applying the Brouwer rule to the assumption. If you do that, then you're going to get, it's not a hypothesis, but it's going to be necessarily possible that possible P. So that's just by 1 and the Brouwer rule. Well, generally, that is not going to feel like a productive approach unless you can come up with a theorem that you could assert either by TI, theorem introduction, or by the N rule, and maybe in conjunction with the K rule, get some value out of that. So, is there a theorem that we have proved recently that connects possible P to possible P? And the answer is that we did, right? Remember, we proved earlier that possible P yields possible P. We actually did that using negation, introduction, and the Brouwer rule. So we can avail ourselves of this theorem, and we can assert that it's necessarily the case that if possible P, then possible P. So that's not by any line, that's just by the N rule. And then if we apply the K rule to this, we're going to create an antecedent that matches line 2, right? So the K rule now allows us to distribute the box. So we've got necessarily possible P yields necessarily possible P by 3 and the K rule. Now you can see how it's going to go, right? Conditional elimination provides necessarily possible P. So that's just a direct proof. So we just proved if possible P, then necessarily possible P. And we did that for fun, but also because that gives us another possibly useful theorem in proving what really interests us right now, which is possible necessary G, therefore necessary G. So we'll proceed knowing that in the background we have these two theorems that might help us out. Okay, so this is what we're going to try to do. We're going to try to show that possible necessary G implies that necessary G And the trick to doing this, seeing how our theorems to be useful, is to realize that the assumption, although it says possible necessary G, you want to just think of this as possible A, possible anything, because that tells us, given what we just proved, is that if it's possible that necessarily G, then it's necessarily possible that necessary G. So notice here that we didn't use the end rule, we used the theorem introduction rule. This is not boxed. It is just the assertion of a theorem that we have already proven, namely again that if it's possible that A, where A now is necessarily G, then it's necessarily possible that A. So that gives us, just by conditional elimination, that it's necessarily possible that necessary G, just by 1 and 2 conditional elimination. Well, now what do? Well, now you want to think more in terms of the end rule. And remember that we also proved that if it's possible that it's necessary that G, then G. So if we were to assert that by N, we would get it's necessarily the case that if possible necessary G, then G. And that would be by the end rule. Again, theorem proven above. Now, can you see why we did that? Because if we now use that great K rule, we can distribute the box and we get line 3 as our antecedent condition, and that's going to give us necessarily G, right? So by K, necessarily possible necessary G, then necessary G for, and the K rule. Again, just simple conditional elimination applied. It's going to give you necessary G, and that was our conclusion. So, according to Leibniz, if it is possible that God exists necessarily, then God actually does exist necessarily. Now, this doesn't prove anything if you don't accept his assumptions, but it's an interesting exercise to try to see which of these that you would actually reject plausibly. And part of the motivation for different modal logic systems has actually been to avoid a conclusion like this. Remember, this isn't inherently about God, it's just about any proposition whatsoever. So it proves that if it's possible that it's necessary that P, then it's necessary that P. Okay, so that's the end of our little introduction to derivation in modal logic, and we'll try to get better at this with a forthcoming homework assignment. Jamata.